Santosh sir, please start now.
Hello. Am I audible, sir?
Yeah, sir, you are clearly audible.
Okay, sir. Sir, good afternoon. Sir, myself Santosh Kumar Tripathi,
Sir.
Assistant Professor in REC Kannauj, Electrical Engineering Department. Shall we start, sir?
Yeah, please.
Okay. Thank you. Good afternoon all, to all. Welcome you all to this program on opportunities and challenges in modern power system, organized by the REC Kannauj, Department of Electrical Engineering. It is my special privilege to introduce Dr. Bhavnesh Kumar, sir, Assistant Professor in Department of Instrumentation and Control Engineering, NSUT Delhi. He holds Bachelor of Technology in Electrical and Electronics from Uttar Pradesh Technical University, Lucknow, and Master of Technology in Control and Instrumentation from the Motilal Nehru National Institute of Technology, Allahabad. Now it is Prayagraj. He earned his PhD degree from the Gautam Buddha University of Greater Noida in area of artificial intelligence controllers for the induction motor drives. With a teaching experience of more than 10 years, he had served GBU, Greater Noida, Airport Authority of India, KNGD Modi Engineering College, Modi Nagar. He has published various research papers in journals and conferences of repute. He has presented his work in many international conferences. He is a member of the various professional bodies such as Institute of Engineers and Electrical and Electronics Engineers, that is IEEE, and International Association of Computer Science and Information Technology, IAC, SIT, ISTE. He is technical reviewer of various international journals indexes in SCI/SCIE. Without further delay, let us welcome Dr. Bhavnesh Kumar, sir, to begin his session. Sir, please, you may proceed for session.
Thank you, Dr. Santosh, for such a nice introduction of me to the participants. Before I begin, I would like to congratulate the coordinators and the REC Kannauj for organizing such a wonderful faculty development program. And such kind of programs are really being beneficial to the scholars and the faculty members. Okay, so to start with, today I have taken up this opportunity and I will be discussing about the solar photovoltaic technologies during this presentation. So let us start the presentation and hope you will be enjoying this. So first, the first thing is that what is the global challenge in this 21st century? We are living in 21st century. So what is the global challenge nowadays? The global challenge is basically you can easily depict from the figures which are on your screen, that you can see that the temperature anomaly which was in the era of pre-industrial era was hardly there was an anomaly, right? It was around 0 degrees centigrade. But if you see in the year 2022, the temperature anomaly has been risen to a quite high level, and it has in fact crossed 1.5 degrees of centigrade. So this has come up as a global warming, in fact. And what India announces for its basically mitigation is the ambitious Panchamrit targets, and it announces it at the conference of parties, that is the 26th conference of parties held in year 2021. So India announces Panchamrit to basically mitigate the effect of global warming or to reduce this global warming. Now let us have a brief over these Panchamrit targets. So India announces its 5 targets to reduce the climate change effect, and the first target it laid down for the India is that India is going to have a net zero emission by 2070. So that means that India will be committed to achieve the net zero carbon emissions by 2070, making making a long-term climate goal to reduce the green gas emissions to the point where they are being balanced out. Now, after this, the second point which India has targeted is the 50% of energy from renewable energy sources. And this target has to be met by 2030. So India has targeted to achieve the total energy generation from the renewables only 50% of that by 2030. Now, within this line of achieving the 50% of energy from the renewable, India has targeted the 500 gigawatt of renewable energy capacity, that is also to be by 2030. So India is aiming to have a 500 gigawatt of renewable energy capacity by 2030, and it is for the net zero by 2070. Similarly, India has also targeted to reduce the carbon intensity by 45%. In this all way to being a greener, India has also targeted to increase the forest cover so that it can neutralize the carbon footprints. So India has given Panchamrit to the world so that it can mitigate the effects of the climate change. So climate change basically refers to the long-term alterations in the Earth's climate pattern, particularly increase in the global temperature over the extended period. Now, it is basically primarily caused because of the emission of the greenhouse gases, such as the carbon dioxide, methane, or nitrous oxide. These gas, what they do, they trap heat from the sun and contribute to the greenhouse effect. And this leads to the basically rise in the average global temperature, which finally leads to or consequences comes as an altered weather pattern and various environmental impacts. Now, what are the causes? So if you see the causes, you will find that the burning of the fossil fuels, majorly for the energy production or transportation or the industrial process, they are the major cause of this greenhouse emission. Now, along with this, deforestation and industrial agriculture and other land use change has also contributed to the greenhouse gas emissions. On your screen, there is the solar radiation spectrum, and you can see that the sun rays which we receive on the earth, you can divide them into the different categories according to the wavelengths. So the shortest wavelength have the higher energy, of course, but we call them as UV, and before the UV we have the X-rays. Now you can see that the maximum intensity waves which we receive on the earth, they comes in the region of visible region. This slide I have put it to show you that how your basically sunlight travels and it comes to earth. So if you see, you can see that while traveling sunlight from the sun towards the earth, it has to cross the atmosphere. When it crosses the atmosphere, there will be some of the rays that will be directly reaching to the earth's surface, and we call it as direct radiation. Whereas from those sunlight, some of the heat is going to be absorbed by the atmosphere for getting the air warm. Now, there could also be a reflected wave that could be reaching back to the space. Now, the atmosphere, basically what it does, it can approximately cut about 50% of the sun's energy that could have reached the earth. And in the atmosphere, this happens because of the scattering and the absorption. The peak intensity of the sunlight at the surface of the earth is about 1 kilowatt per meter square that we even consider for the standard test conditions. Now for the light waves, the energy associated with the wave increases as the frequency or the wavelength decreases basically. Now consequences of this climate change, we all are observing it, and on the one way or the other, we are basically a sufferer of this. We are a victim of this. What are the consequences? Consequences are the extreme weather events. So global warming has been linked to more frequent and severe extreme weather events such as hurricanes, droughts, floods, and the wildfires. Along with this, we are also seeing a rise in the sea level. So as our global temperature is rising, glaciers and the ice sheets are melting, and it is being leading to the rise in the sea level. This is also posing a threat to the coastal communities, ecosystems, and the infrastructure. Along with this, the ecosystem is getting disrupted, obviously. Ocean acidification is also being now happening at the higher rate because of the rise in the temperature. The increased absorption of the CO2 is happening, and this has been leading to the acidification, harming the coral reefs and other marine organisms that rely on the calcium carbonate structures. Along with these, the least but the not the last but not the least is the health impact. You might be observing that due to the global warming, there is a direct or indirect impact on the human health, and it affects the human health through heat related illness, increased prevalence of the vector-borne diseases, or reduced air quality, and the food and water insecurity. So there are numerous consequences of this climate change which we are seeing. Now, if we see the behavior, if we want to see the progress of India towards this the renewable energy generation, so we can compare it. I have compared the 2 years data. One is from the November 2020 and other is of November 2024. So if we see the data of November 2020, you will find that the total installed capacity in 2020, the major portion has been coming out of the thermal energy generation system. So thermal use the coal as a major portion. So you can see that 62% was being the 62% capacity among the total installed capacity in 2020. But in 2024, the thermal capacity has been reduced from 62 to 53%, almost 9% has been cut down, has been reduced. But we had to get this share from the others. So where from this share has been taken? If you see the renewable energy share in 2020, you will find it that India was having a 24% renewable as an installed capacity among the total installed capacity, whereas India has increased this renewable energy capacity to 35% in 2024. So almost 11% increment in the renewable energy generation we have seen over the last 4 years from 2020 to 2024. Now, among these renewable energy generations, India is our location is on a location, or we are having a location on the earth where we receive a good amount of sunlight. Secondly, we also have a quite large coastal line, so that we do also have a quite good amount of wind energy resource. So if you see the pattern or the mix of the energy or the installed energy system among the renewable energy sources, you will find that in November 2020, the solar power installed capacity in India was 41% among the renewable energy sources we are talking about, whereas the wind power was around 43%. Now, if you see the share in 2024, you can observe that India has energy capacity of solar power from 41% to 60%. Now the installed capacity in 2024 is 60% of the total. So total 60% of the total from the renewable energy sources comes from the solar power. So this is, and the reason is because what we have is this solar resource. If you see the map of India, which is solar resource map, you will find that because we are being located in the equatorial belt, we receive our sunlight in almost every part of this country. Also, from throughout the year, we receive this sunlight, and almost 300 to 330 sunny days are there in a year, which is being equivalent to the 5,000 trillion kilowatt hour of energy. In fact, average solar incidence stands at about 4 to 7 kilowatt hour per square meter per day. That leads to the annual global radiation vary from 1600 to 2200 kilowatt hour per square meter. So with this much of means we are being lucky enough that we are having quite good amount of solar energy resource in India. We receive a sunlight throughout the year. So that's why the government is also focusing on utilizing this potential which India have because of this, because of its location over the earth. Now, how can we harness this? We all now being familiar that there is a technology what we call as the photovoltaic technology, and with this photovoltaic technology we can harness the solar energy and we can convert the solar energy directly into the electrical energy. Now, due to various reasons such as scarcity of electricity, pollution concerns, and rapid depletion of conventional energy sources, the applications of this PV is increasing. However, if you see the solar energy, there are some pros that it is abundantly available, it is inexhaustible, it is also clean and cheap. However, if you look towards the cons, you will find that this solar energy is tenuous. It is undependable and expensive beyond practicality. I will tell you why we are saying so. So basically, you can see that it is intermittent in nature. Solar energy is intermittent in nature. It will only be available during the daytime. In the night time, will not be having any solar energy. Also, when in the daytime we'll be having solar energy, this will be varying throughout the day. In the morning to dawn, we'll have a lower solar energy and we're going to have a maximum of the solar energy in the afternoon. Now, the photovoltaic technology, if you see, it basically uses, and its simplest or the smallest unit is this cell. This cell takes on the solar irradiation and it converts it into the electricity. Now, this, if you see a cell, it hardly produces a voltage of 0.7 and 0.8 volts, which is of any practical use. So what we do is we take number of such cells, we connect them in series and more parallel to have a quite usable voltage level or the current level. These modules now can further be connected in series and parallel to form an array. So in this way, finally, as per the requirement of the load, we decide to have the number of modules and the connections among those modules, that what should be the connection. If suppose we are having a PV module, one module, its rating is suppose 12 volt voltage rating, and we want an application to be run that requires a 36 volts. So what we'll be doing is we'll be connecting the three modules in series such that we can have a 36 volts of the output voltage. Similarly, there could be a current rating that your load may be requiring. So to satisfy that load requirement or current requirement of the load, we may connect the panels in parallel. So in this way, we can get the PV array being constructed depending upon the requirement of the load, and we can have a series parallel combinations. Now, if we see the historical developments, you will find in the history that it was around 1839 when a French physicist called Edmond Becquerel, he discovered the photovoltaic effect. So photovoltaic effect was discovered in 1839. It was very near to the when Faraday discovered the electromagnetic induction law. However, it took around 50 years to produce a first photovoltaic cell, and selenium photovoltaic cell were first built, and that was only having an efficiency of 1 to 2%, and that was that time being adopted in the field of photography to just for measuring the light or to operate the shutter of your camera. Then after 1880s, Almost then again, with the 60 years, the Bell Telephone Laboratory, it resulted in a one silicon photovoltaic cell that was a 4% efficient. Means it has doubled the efficiency. But again, if you see in figures, the first cell which was being built by this Bell Telephone Laboratory was 4% efficient. But soon after the 4% efficient cell, Bell has gotten, they succeeded to get a better version of that, and they enhances the efficiency to 11%. So in 1954, Bell claimed that they are having a solar cells that are the silicon solar cells, and it can convert the energy with a 11% of efficiency. With this cells, the US Vanguard, which was the space satellite of the US, used the small photovoltaic cells to power its radio. And success was such a grand that since then, the PV panels have become an integral part of space programs ever since. Now, if you see a satellite, you will find a solar panels over there. So for the first time, it was used with the Vanguard space by the US satellite mission. Now we are standing in 2025, and now you can see that the progress in efficiency solar cells has made, and now the efficiency is almost about 30% or 25 to 30% of these cells. That means if we are having a 1 meter square of solar panel and 1000 watt per meter square of sunlight is being falling on it, then with the 30% of efficiency, we'll be able to get 300 watt of power from the panel. This is the graph about the progress in the efficiency which has been there over the years since from 1980s to 2025, and the graph is basically showing the progress in the efficiency of the crystalline silicon cells. So you can see that that the NREL is claiming that almost 27% efficient cells are being available now that can harness the sunlight and can produce the electricity from it. So with the 1000 of watt per meter square of sunlight, now you can generate 250 or 270 watt of the power. If we see the photovoltaic applications, you will find that there are numerous applications, and in fact, you can divide them into the two categories. One called as the on-grid, which is there being on your screen, means your PV system is going to be connected to the grid, whereas the other ones which are called as the off-grid. Now, if we see the off-grid applications, you'll find that the water pumping is one of them. So nowadays, people are using this solar photovoltaic based power water pumping systems. Also, space is the one, and the transportation industry or transportation sector is also trying to utilize this solar cells for making the vehicular technologies, for developing the vehicular technologies. Okay, now if we go for the specification, suppose we want to buy a solar panel, then what specifications we'll be looking for? If you see, and if you go to buy a solar panel, they will give you one data sheet. And if you see the data sheet, you will find the following important parameters which your manufacturers has mentioned. Now, it has mentioned that nominal power output is going to be 235 watt. It's fine. But before reading this 235 watt, you should read this STC, which is being marked star. And STC is nothing but it is standard test condition. And standard test conditions are being mentioned in the last or at the end of this on the last of this slide, that this standard test conditions means that the irradiance which your panel is receiving should be 1000 watt per meter square. Also, the temperature should be 25 degrees centigrade. Now, if manufacturer is mentioning 235 of watt, it doesn't mean that your panel will be giving the output of 235 watt every time. They are saying that your panel will produce the power of 235 watt under the standard test conditions. Okay. Now, while giving you 235 watt of power, they have also mentioned the different things. One is the voltage at Pmax, other is open circuit voltage. If you see the data sheet, you will find that there are the two voltages being mentioned. One is the voltage which is VMPP and other voltage which is VOC. Now, what is this? What is VOC and what is VMPP? If you see the characteristic of a solar cell, you just see the current versus voltage characteristic.
वो भी किया बहुत सही वाला, वो यूट्यूब किया है, मैंने कन्नौज वाले किया है।
अरे
इनके अलावा
Dr. Dilip, please, can you put your mic on mute? Thank you. So basically, if you see the IV characteristic of a solar cell at a particular irradiance, suppose we are looking for a green color curve, and this curve is with 1000 watt per meter square. You will see that we are having a current almost, that is the maximum of this current, and it is when we are having 0 volts. Now, in electrical engineering, 0 volts means we are having a short circuit among the two ends or the 2 points. That's why if you mark this current or this point on this y-axis, we say this is a ISC or the short circuit current. Whereas if you travel along this curve, you will find that this current is being not so much reducing up to this volts, that is around 30 volts. But after this, you will be observing a sharp decrement in the current, whereas voltage is being not so much reduced. At the end of this curve, when their current will be 0, then current 0 means that the 2 points are going to be open circuited. That's why if we take this point, this point is being marked as VOC. So if we see the curve on the one end, that is on the y-axis, we are having a short circuit current that is being given over here, short circuit current, that is the last entry, and the VOC, that is the last entry on the x-axis, and that VOC is being given as 37.0 over here. So these are the two voltages which are being marked. Now, what are these VMPP and IMPP? If you again see this curve, and if you try to plot the power versus voltage curve for this curve only, for the green curve only, you will find that power is going to be 0 at the beginning, at the ISC, because ISC is there, but voltage is 0. Power is nothing. It is the product of V into I. So power is going to be 0 at this point when your current is at short circuit. Also, power is going to be 0 at the point when you are going to have a VOC. So power will be behaving like will be having 0 power at this end, and slowly it will be increasing. Finally it will be reaching the maximum value, and then will be coming back and reducing it to 0. So you will find that over this IV curve, there will be a point where power is maximum. And corresponding to that maximum power point, there will be having a one current level and a one voltage level. That current level is being marked as IMPP, whereas that voltage is being marked as VMPP. So these are the different entries which manufacturers give, that what is going to be the VMPP, what is going to be IMPP, and what is going to be VOC and ISC for this particular module, which will deliver you a 235 watt of power under the standard test conditions. Moving ahead, we know that in the literature, it is not always, in the literature, we do have a different kind of equivalent circuits for the solar cell. And it is the most common equivalent circuit of a solar cell, where we use a single diode motor. And from this, we can easily get the current equation which describes this current, which is the PV current, and equation from your screen. Now, why these RS and RSH are included? you can see that what are those effects. If we increase the RS, the characteristic, you will going to see changes like this, which are there on your screen. Whereas with the RP, which is nothing but is the RSH, if you increase this, there you will find to have the change in this pattern. Now, why do we need MPPT techniques? Why do we need? Because what happens is your solar radiance is variable. Solar radiation variable means the amount of sunlight hitting a solar panel fluctuates throughout the day, and it may fluctuate due to the weather or the time of the day or the seasonal changes. So this is one of the reason we are looking for the MPPT techniques. Second, also your temperature is going to affect the PV characteristic or the IV characteristic of a solar panel. If you see the characteristics which are being there on your screen, there it is the power versus voltage characteristic. Okay, in this power versus voltage characteristic, you can see that for different insolation levels, you are going to have a different maximum power point, and this power point is going to be at a different point of voltage and the current. So we need a algorithm so that we can always harness the available maximum power from the solar panel. This is the one thing. The second thing is we also know that on the earth, we are around at a latitude of 30 degrees. Earth is near to this 30-degree. So sun rays which should be falling on the solar panel, we know that for lesser reflection, it should be perpendicular. So we always tilt our panels of about this 30 degrees so that we can receive the sunlight maximum. So because of these reasons, what we do, we use two kind of approaches for maximizing the energy harvesting. One is the optimal orientation and the tilt. Now, the sun tracking systems is basically used to adjust the orientation of the solar panels throughout the day and across the seasons. Now, this sun tracking systems, these are the mechanical systems, and it can be single axis or dual axis, because we know that if we'll be facing the sun always, and then we'll be receiving the maximum of the sunlight. The second thing is the fixed orientation, because what happens is when we use these sun tracking systems, some of the energy is being consumed in orienting these panels towards the sun, and that energy consumption in many cases becomes more. Although research shows that you can increase this efficiency and you can harness the energy, right? But in many cases, it has been found that the energy which these systems are being consuming is more as compared which we are gaining. So in maximum cases, fixed orientation panels are being used, and for that system, they do not use tracking. Panels are being installed at a fixed tilt angle based on the latitude of the location to maximize energy capture over the year. So the first approach is to basically make a face of your panel towards the sun so that it can harness maximum of the energy. Now the second approach is about the maximum power point tracking techniques. What happens is we have seen that PV, your solar panel, although will be receiving 1000 watt per meter square, but the power from the PV panel is going to vary along with the load. So what you want is, already you know your panel is 20 to 30% efficient. Already you are wasting the 70% of the sunlight. You are not being able to get it. But what you try to get, or what you try to do is at least whatever energy you are getting from the solar panel, you can harness all of it. So maximum of it. So that's why maximum power point tracking algorithms are being used, and these adjust the voltage and the current to ensure that the PV system operates at its optimal maximum power point despite of the environmental conditions like temperature change or the shading or the sunlight intensity change. So these MPPT algorithms ensure the optimal operation. This is the basically a figure showing you the dual axis sun tracking system. You can see that this dual axis sun tracking systems do have the capability to rotate in either from east to west, because our sun being look, if we see the sun from the earth, it will look like to you that your sun is moving from the east to west, although it's not true. Your sun is being fixed and your earth is revolving and rotating around the sun. Also, the dual axis sun tracking system, it has capability to move from north to south and south to north. So this is basically a figure showing you about the dual axis sun tracking system. If we talk about MPPT implementation, you will find, and you will, in many of the researches, you will find that they use a DC converter. So a converter is being used in between the load and the PV panel, and this converter matches the it basically matches the impedance of the load to the source, that is a PV panel. And in this case, what we do is we try to use the MPPT algorithms that identify that point where that impedance matching is being happening. For any MPPT algorithm, two parameters are very pivotal. One is the settling time and other is the accuracy. So you will also find that the persons who are proposing these MPPT algorithms, they are trying to check their performance on the basis of the settling time and the accuracy. Accuracy here means how close it is to the actual value. Means if suppose your panel is being capable of delivering 230 watt, so how close to that 230 watt your MPPT algorithm is being able to drive your PV system. So that basically makes the accuracy of your system. And first, and the other is the settling time. Suppose sunlight is being changing due to some reason. It may be because of a cloud which has come for a moment and now it has been gone. So the time when over your panel the cloud was there, your panel might not be receiving the full sunlight. Suppose your panel was receiving a 50% of the sunlight, but after a few seconds this cloud has gone and again your panel is being receiving full sunlight. The situation is like that earlier your panel was receiving 500 watt per meter square installation, and now suddenly, so with this sudden increment or decrement in the sunlight, how fast your MPPT algorithm is reacting, that gives you an idea about its settling time. And settling time basically is the measure of how fast your MPPT algorithm is working. See or try to have the conventional MPPT algorithms, you will find the following names in the literature. One is the perturb and observe. Perturb and observe means we try to give the perturbation in the voltage and try to observe the power. So where the power will be maximum, will be moving in that direction. If your power is increasing with the increment in the voltage, will keep on increasing the voltage. If power is decreasing, will reverse the direction. Means if your power is decreasing with the increment in the voltage, we are going to reduce the voltage in the next step. So this is the way your perturb and observe MPPT algorithm works. Second is the incremental conductance. It is nothing but it is also a version of a P&O algorithm, and they both tries to utilize the fact that if we are having a slope and there is a one peak, so over the peak the slope is going to be 0. So they utilize of the fact that del P by del V on this PV curve, if we see at this point the dP by d is going to be 0. So both utilize the incremental conductance and the P&O. They both utilize the concept that the dP by dV will be 0 at the maximum power point. Along with these two, people has also given the MPPTs, which are called as the fractional open circuit voltage. And this has been given knowing the fact that if your panel is being receiving the sunlight, which is being lesser than the previous one, and suddenly if it is being again and again reducing, you will find that the voltage or the VMPP point is not being changing in a quite high range. It is being changing in a narrow band. So if we fix, even if we fix this voltage and this band, if suppose this is the VOC, this is the VOC for this red curve, that is around 38 volts. And if we take this VMPP, which is 30, 30 means ki around, if we multiply the 38 by 0.8 around, then we will be having this 32. So if we fix even this 0.8 as a K, then at every moment or with every irradiance, we are going to receive the maximum power, because we'll be able to operate the P panel on the MPP point. Not exactly, but near to the MPP point. Now, how can we implement the MPPT? There are different ways of implementing a this P&O MPPT. MPPT algorithm, as we already have discussed, that it is being designed or developed based on the fact that dP by dV variation is going to be 0 at the MPP point of the P module, right? So duty cycle is being varied in order to track the peak power, and the change in the duty cycle results in the change in the voltage. So duty cycle of the buck converter, which we have seen, buck or the boost or the any kind of DC converter which you are utilizing to implement the MPPT, what do we change the duty cycle of that converter? We do understand from our previous learning that in the chopper circuits or the converters, which are DC converters, the output voltage will have a relation in terms of duty cycle to the input voltage. So if we talk about a boost converter, we know that the output voltage V0 is going to be 1/1 minus D of V in, where D is the duty cycle, and duty cycle means the ratio of the on time of the switch to the total time. So on time means the time for which you keep that switch on, to the total time means the on time plus the off time. So this gives the duty cycle. Similarly, for the buck converter, the output voltage and input voltage are also related. And in case of buck, the relation is that your output voltage is going to be D times of the V input voltage. Similarly, you can use a buck boost converter as well, and multiple converters are being proposed for the MPPT implementation. You can use any of that converter to implement the MPPT. Same is with the incremental conductance, and that also utilize the same concept that del P by del V. It is going to be 0 at the MPP point. So these algorithms are really easy to implement. And here is the flow charts of both the algorithms. Those who are interested in reading this, they can find it in many literatures. These are the schematic diagrams of implementing a constant voltage MPPTs or constant current MPPTs. First schematic is about the constant voltage MPPT, where we do understand that your voltage is not going to vary in a wider range, or even for a greater change in the insolation level. Your change in the voltage will be in a narrow band for the change in the irradiance. So we can implement it like that way, or this way, or this way. This could be the two structures in which you can implement the MPPT. You can use a PI controller, or directly you can generate the duty cycle for your converter by taking the input of the VPV or IPV, or simply the VPV. So depending upon the MPPT algorithms, there may be a requirement of voltage as well as current, or a voltage only or a current only. So that will depend upon the MPPT algorithm, that how many sensors you require to implement a MPPT algorithm. Now, if you see these conventional algorithms, which are MPPT techniques, there are multiple limitations that they are slow in response to the sudden changes. Secondly, oscillations around the MPPT are more. The major limitation of these conventional MPPT algorithms are the fact that during the partial shading conditions, they lead to the tracking of local maxima, means they get trapped in the local maxima. What happens with the partial shading condition is if we are having a partial shading means suppose you have taken a two modules and you have connected them in series, but due to any of the reason, one of the panel suppose is receiving a lesser insolation than the other one. So what is being happening in that case is that the panel which will be receiving lesser insolation is going to generate lesser current. But the two panels, the other panel is also being connected in series. So in series connected panels will going to have a same current. So that restricts the panel which is receiving a lower insolation will be generating lesser current, and that will be restricting the current in the other panel as well. So because of this, the total capacity of the string gets reduced. Also, if we see the PV curve of, in that case, you will find that there are the multiple peaks are occurring as being shown by this purple curve. This purple curve is for the shading condition, whereas blue curve is for the uniform shading or uniform insolation. So when shading occurs, you will find that there will be a multiple peaks. The peaks could be 2 or 3 or 4 depending upon the array size and the shading condition. So if you see that there will be a multiple peaks, and you know your conventional algorithms works with the concept that the power is going to be maximum where the slope will be 0. So slope is going to be 0 at this point also and at this point also. So it may happen that your conventional algorithm may get trapped with this local maxima, and with the trapping at this local maxima, you may be having this much of power loss. So this is going to be a power loss, and power loss means per second you will be losing this much of voltage. So that's why these conventional algorithms during the partial shading conditions are very inefficient. They reduces the efficiency of the overall system. That's why people are looking towards the intelligent MPPT algorithms that can differentiate between the maxima, that is the local maxima, and the global maxima. Maxima, both are the maximum points. We are having a maximum at this point also, at this point also. But if you see, the global maxima is occurring at this point. However, then that will be a local maxima. So people are working on the algorithms that can detect this local maxima and the global maxima, and that can differentiate between the two. That where is the okay, I think that's enough for today. Dr. Santosh. Dr. Santosh. Should I continue or can I stop it here? Hello.
Hello.
Yeah, hello.
Sir, you can continue if you are comfortable, sir.
No, you tell me whether should I discuss some more topics or shall I be closing at this point only? Because I'm having a meeting at 4:45, so I can continue for 10 more minutes if you want.
Yeah, sure, sir. Sure.
Okay, so let me continue for 10 more minutes. Now, the problem with the conventional algorithms are that they are not being capable of differentiating between the local maxima and the global maxima in case of partial shading conditions. So what people are looking for is the intelligent techniques, and while searching for the intelligent techniques, people has found that fuzzy logic can help in this case, and you can build your MPPT with the help of the fuzzy logic. I think all do understand that fuzzy logic, they work with the linguistic variables rather than to be numbers, and we have the different stages in the fuzzy logic controller. That first what we do, whatever inputs, numeric input we get, we try to fuzzyfy that, and we try to have the linguistic variables. Then based upon those linguistic variables and the framed rules, we take on the output. Based upon the input, we decide that, and the rule base, we decide that what should be output. Finally, your plant only do understand the numeric data. So the defuzzification process we had to do, and finally with the defuzzification process, we'll be having a numerical data. So we give the numerical data as an input, we get the numerical data as an output, but in between, the fuzzy logic controller process the things in linguistic variables. So people had tried a lot in utilizing this fuzzy logic controller for the MPPT, particularly in case of the shading scenarios, partial shading scenarios. One of such case I am being showing to you, and this work was conducted by my student, where he tried to have the he tried to identify the area of the shading in which the shading could have been occurring, or the global maxima could have been occurring. So what he did is he taken a PV array with 3 series configurations as being shown on the screen. So there are the 3 PV panels. One is IR1, IR2, and IR3, and all 3 were connected in series. And he tried to have he have seen that what is going to be the PV characteristic for different irradiation patterns. Suppose first one is receiving 200 watt per meter square, other one is receiving 300 watt per meter square, and the third one is being receiving 900 watt per meter square of insolation. What is going to be the PV curve? So he made 3 patterns, 1, 2, 3, and he tried to have the PV curves for the 3. So for these 3 cases, if you see, for the pattern 1, he found that the global maxima is occurring in this region. So he also have divided this whole range of the voltage into 3 regions. So for the pattern 1, in the region 1, we were having the global maxima. But for the pattern 2, if you see, the global maxima was occurring in the region 2, and for the pattern 3, the case was such considered and framed that your global maxima occurs in the region 3. So the objective was to design a fuzzy logic controller that can find that in which region your global maxima is going to occur. So he tested this and he found these results. And with these results, he declared that yes, with the designed fuzzy logic controller, your controller or MPPT controller was able to identify the global peak in every case, whether it is a pattern 1 or a pattern 2 or a pattern 3. Your MPPT algorithm will be able to track the global maximum power point. So in this way, he designed this MPPT controller that was intelligent and that could differentiate between the local maxima and the global maxima. Although the settling time which the controller or MPPT algorithm was taking was quite high, but yes, your solar photovoltaic panel was able to, we were able to harness the maximum point during the shading condition or partial shading condition. Now, if we see the latest advancements, you will find that now due to the crunch in the space, or the people are trying to put more solar panels, and they are coming up with the concept of solar tree. And one of the research has shown that with this solar tree, we'll be able to have more power. Will be able to have a more power than the flat module power or flat module cells. So what one researcher has done, he has put the same number of PV modules in a flat module case, whereas he has taken those also and pasted over a tree, and he tried to have the IV characteristic for both cases. He found that the IV characteristic with blue is for the sunflower pattern. This is the sunflower pattern. Whereas for flat module, this is the case of IV characteristic. And you can see that will be having more power, means will be generating more power if we are putting the panels in the form of sunflower. And this is the evidence of this, that we're going to have a more power. That is, for the same number of panels, you will be able to have around 18 watt of the output, whereas for the flat it is only around 15 or 13 watt around the energy or the power. Now these are the important websites which you can go through, and you will be finding various important information if you want to see. Thank you for listening me, and that is all for today's lecture.
Thank you, sir,
Now
for
I am
this
open for the
insightful
queries.
session, sir.
I am open for the queries. If you want to have, if you are having any of the query, you can ask to me directly. Anybody having any query?
For this insightful session, sir.
Hello. Hello.
हाँ
Sir,
बताइए डॉक्टर साहब.
Sir, thank you for your interactive session. Sir, complete हो गया sir?
हाँ कंप्लीट हो गया डॉक्टर साहब. अगर किसी को कुछ पूछना है तो पूछ सकते हैं.
हाँ, मैं थोड़ा सा अनाउंस करने वाला हूँ. तो dear participant, you have any question, please ask. Ask to sir. The session was very nice. Necessarily, definitely you will benefited from this particular session. But dear participant, if have you any question, please ask. Thank you, sir. I suppose there is no question from participants.
Everybody
Thank
has
you
conceived all the things which I tried to make them understand.
Yeah.
So thank you,
Yes,
Dr.
yes.
Saab, again. And thank you for the team for giving me this opportunity. Okay.
Okay.
Bye-bye and have a nice day.
Thank you, sir.
Thank you, sir.
Okay.